Okay, so we were dealing with amortized analysis, right? Amortized analysis, and in that amortized analysis, we have seen this incrementing the binary counter, okay, with aggregate analysis. And today we will see that how that problem, that incrementing a binary counter, can be analyzed using potential method. Okay, so using potential method, we will be analyzing this potential method, right? So this today we will be seeing this potential method, right? And so for this, what we got to do is we define here, we define the potential of the counter after the ith increment operation to be bi, and this potential of the counter, that is bi. And what is this bi? Bi is the number of ones in the counter after the ith operation. So number of ones that is there in this after this ith operation, which will be stored in this bi data structure. Okay, so as we have seen this we have to maintain a data structure, and then this that will be having a phi function which will be mapping it to a real number. Okay, so that happened in stack operation as well. Okay, we were maintaining that how many number of elements are there in the stack after the ith operation. So here what exactly happening, so whenever we are here and then whenever we are here, okay, so you see the ones are changing, number of ones are changing whenever we are changing state. That means changing whenever we are having one increment operation. So here also we are having it's changing. Okay, so here you see the number of ones are changing. So that could be a clue that how we can set this data structure. Okay, so that's why this bi is defined as the number of ones in the counter after the ith operation. So now let us compute the amortized cost of an increment operation. Suppose that the ith increment operation resets ti bits. Okay, resets ti bits. So you see this whenever, say from here I am going to here. Okay, going to here, then you see this will be resetting, this will be resetting, right? So suppose the ith increment operation resets ti bits. So whenever we will be having the ith increment operation, some bits will be reset. Okay, so ti will be counting that thing. So it is resetting ti number of bits. The actual cost of the operation is therefore at most ti plus 1. The actual cost is ti plus 1, since in addition to resetting ti bits, this resetting ti bits, it sets at most 1 bit to 1. Okay, so you see this, it is resetting, and it is setting. So 1 bit is set to 1, last bit, right? So the actual operation, actual cost, the ith operation, ith increment operation will be incurring is at most this ti plus this 1. Okay, some bits will be reset and some bit will be we will be setting some bit. Okay, So now this if bi equals to 0, if this bi, that means the ith increment operation is equal to 0, right? So that means all the bits have been reset. That means we are starting to recount again. So we have reached to this say 111, and then we are going back, as this is modulo counted, so it will be going back to this 0. Okay. So in that case, then the ith operation resets all k bits. So all 111 will be reset to 000. All k bits will be reset, and in that case, so if the all bits, so what was bi minus 1 at that time? If bi equal to 0, what was this bi minus 1? Who will be telling what was this bi minus 1? If bi becoming 0, that means all bit we had to reset. So what was this bi minus 1? Who will be telling? Is anybody listening?
Yes, sir.
Who are you talking?
Sir, Saurabh, sir.
Saurabh, can you tell me? So bi minus 1, that means before the increment operation, how many number of ones were there? So how many number of ones were there? If bi, after the increment operation, bi becomes
0.
0. No, no, after
The
the,
number of 1 is 0.
no, no. After increment operation, bi becoming 0. So what could be this bi minus 1? So that it could be
1.
0.
Minus
Entire
1.
BI will be 1 1.
All ones, that means k number of bits. So that was k,
Yes, okay.
isn't it? So
Mm-hmm.
that is equal to this ti. That means these many number of bits we had to set, we had to reset. Okay. So if bi becoming 0, then bi minus 1 was k. That's why all bit became reset. Okay. So that means ti, we are resetting. Okay. So that is a special condition. But the thing is that if bi greater than 0, if bi at any intermediate stage, what is happening? What is happening then? Bi should be what? So bi equal to this bi minus 1. That means the number of ones that was there previously, right? Number of ones that was there. So think about this, and this. Okay. So this is the number of bi. Okay. After the increment operation. So now this bi minus 1 was what? 2, right? So this bi will be what? Bi minus 1, what was before, and then how many bits I reset, that is this ti. Ti number of bits will be reset in this increment operation. That means bi number of the number of ones that will be decreasing will be by ti. Okay, so those many number of ones will be decreasing because we are resetting those many number of ones. So we have to subtract from bi minus 1 what was there. That means ti minus number of ti number of ones will be reset. Okay, so that means those many number of ones will be decremented from bi minus 1. And then during this reset operation, also one in addition, we have to set one bit. We have to set one bit, this bit we are setting. So we have to have a plus 1 here, right? So this will be the number of ones in bi. What was before? How many we are resetting? That we have to subtract. And then on the way, we are setting one bit as well. So plus 1. That means this will be again incremented, the number of ones. Okay. So this is in either case we can say this bi is less equal to this bi minus 1 minus ti plus 1. Okay. So this is the case we are having. bi is less equal to this many numbers. So this you can check from here to here to here, okay, what is happening. So what was bi? What was bi I minus 1 in this case? That was 1, right? Number of ones was 1. And then what was we are how many number of bits? So 0 1 0, okay, right? So 0 1 0, and then how many number of bits from 0 1 0 we are reaching to 0 1 1, right? So how many number of ones we had? We had 1. So bi minus 1 was 1. Okay. And then how many number of bits we are resetting? Can you tell me how many number of bits we are resetting here?
1
1? Is it?
or 0?
0. Yes. So 1 minus this 0, right?
Plus 1.
And then plus 1, right? Plus 1. So in this case, so bi is equal to this. Bi, how many number of ones we are having after the increment operation? Bi equal to 2. Okay. So bi, this 2 and this 2 we are having equal. So in this case is equal, right? But in this case 0 1 1, in this case what is happening? Let me check. So we had bi minus 1, that was 2. Okay. So in this case, and then what is this ti? How many bits we are resetting? How many bits we are resetting?
2.
2. Okay. And then plus 1 will be there. Okay. So 2 plus 2 minus 2 plus 1. So that is equal to 1.
1.
So we can say that is again equal. Okay. So in this way we can say this bi is less equal to this bi minus 1 minus ti plus 1. So you figure out when it can be less than. Okay. When it can be less than, right? Whether bi equal to 0 case it will be there, or in between any other case whether this less than condition is getting satisfied also. Okay, so that we can write. We can go by this bi equals to upper bound case equal to bi minus 1 minus ti plus 1. That way also we can go. Okay, so now what will be having? What will be the potential difference? Phi di minus this phi di minus 1. That will be equal to, that is less than equal to this. So instead of this, so it will be bi minus this bi minus 1. So what is bi? That is less equal to this, so that is plugged here. So bi minus 1 minus ti plus 1 minus bi. So bi minus 1, I minus 1, bi minus 1 will be cancelled out. So it will be 1 minus this ti. Okay. So 1 minus this ti. So this potential difference will be upper bounded by this quantity 1 minus ti. Right. So now we know this amortized cost of per increment operation. So with this formula, this is the actual cost and the difference in potential. Okay. And what is the actual cost that we have calculated? Ti plus 1, because ti number of bits will be reset and 1 bit will be set. So Ti plus 1, and then plus what will be the potential difference? 1 minus this Ti. So now if we simplify, so Ti plus 1 minus this Ti. So this Ti will be cancelled out, and 1 plus 1 will be equals to 2. So the amortized cost will be upper bounded by these 2. Okay, that means constant. So how many such increment operation will be performing? How many such increment operation will be performing? Who will be telling? Except Shora. Some others should come up and tell. How many such increment operation will be performing?
Sir, you so could you just take the cursor somewhere like
What?
yes, sir.
How many such increment operation will be doing? One increment operation we have seen. How many such any arbitrary increment operation we have seen? So how many such increment operation will be having? So we will have n increment operation, that is sequence of n increment operation we are having, that is already told. So
Yes, sir.
So the amortized cost of per increment operation is 2. So for order of n number of increment operation will be that should be multiplied by 2, because each one will be taking constant or order of 1. Right? So order of this will be again order of n. So this amortized cost, and also it is shown here that if the counter starts at 0, then phi d0 will be equal to 0, phi d0. So phi of d0, that means what will be the number of ones when we are starting? Phi of d0, that will be 0 definitely. So this is the case, number of ones is 0. And since phi di greater equals to 0 for all ones, okay, for all I, that means for all other increment operation you are seeing at least one is present. Okay. So phi of di will be greater equals to 0 for all I. So that was the condition that has to be proved for getting that this Ci cap is the actual Ci cap is the upper bound of the actual cost. Okay, and that also we have argued. So that's why this amortized cost is order of n, right? Yes, amortized cost of n increment operation is order of n. But if we could have a naive worst case analysis, then we have seen that it is order of nk. Okay, order of nk, right? And if k is order of n, then it is order of n square, right? So that is what that is the way we can analyze this binary counter. And here it is shown, here it is again given that the potential method gives us an easy way to analyze the counter even when it does not start at 0. Okay. Say it is starting at 1 or it is starting at 2, and then increment, we are having an increment operation. Okay. So in that case, what is shown here, shown there in CLR is that this amortized cost will be equal to 2n minus some bn. So by using this formula and then taking its summation. Okay. So 2n plus say b0, and it can be shown that this is order of n and this is order of n. Okay. And then this will be cancelled out, and then this order of n will be remaining. Okay. So that way maybe it can be shown, it can be argued like that, so that you you read yourself, okay, from the CLRS book. Okay, so this is for this potential method. Okay, this potential method, and now we are going. So this amortized analysis with aggregate analysis, we have seen two examples. With potential methods, we have seen two examples. One exercise is there called this dynamic table. Okay, so that example is there in CLRS, and this is a very good one. Okay, dynamic table also, this is a very good one, and you should study that as well. So in that this dynamic table, what happens is whenever we are assigning array, okay, and we don't know a priori how many elements will be there in this array. Okay, so initially what we will be doing is we will start initializing two elements array, right? Two elements. That means as if two elements will be coming. That means the data is coming on the fly, online, in an online fashion. Okay, we are not sure about that, how many ultimately will be coming. So it is many a time you do the programming like this way, that okay, a equal to say 1000 elements, like this, 1000 elements, right? And so here, if priori you are accumulating, or you are assigning this many memory for this much memory for this array A. So in this dynamic table, we are solving this problem. Okay, so we don't know a priori how many elements will be coming, whether it is 1000 or 2000, what. So you'll be starting to have its dynamically being allocated. So A equal to 2, and then whenever first two elements have come up, say with these two values, and then when the next element to be included, so at that time this this A, again it will be, this A will be created with this or A prime will be created with 2 times 2, that means double the size, and then first this one will be copied back, this one, and then this 30 will be added. Okay, so next time whenever the for say some other element will be coming, so this may be entered here without copying and doubling. Okay, so this is, you see, and now say this has been filled up, and then another element 50 to be inserted. So in that case, again it will be created with 8 elements round. Okay, so these elements will be copied back here first, and then this 50 will be added, and then next 3 elements which are coming, that will be directly added. Okay, here, and then there is a question of doubling coming up. Okay, so you see, whenever we are inserting elements, many a times that insertion is taking place order of 1 time. Okay, many a times, but some point of time when this array, whatever we are having allocated so far, is filled up, then it is taking a bulk amount of, then this array insertion is becoming expensive. In that case, we have to copy it back so far the elements we have done, and then we have to double this and then copy it back, and then this one to be inserted. Okay, so you see, for a sequence of n insertion, many insertion operations happening with order of 1, and few are expensive, say order of k, right? Few are expensive, a few. So you see, this is a potential candidate, as we know this, whenever in sequence of operation going on and a few of the operations are expensive and bulk of the operations are inexpensive, then we have to go for this amortized analysis, right? So that in this dynamic table exactly that is happening, right? And you read it from CLRS, right? So that is there. You should read it yourself. But the idea I have told you, and with this idea now you read it, then it will be easier for you to follow CLRS. Okay. Okay. So now we'll be going to this another one that is called, as we were discussing, that master theorem is not discussed, so we'll be discussing master theorem, right? Now, will it be possible to have a class at night today? So, or tomorrow, maybe tomorrow night, not possible maybe. Today will it be possible? Saurabh,
Tomorrow only, sir.
today possible?
Today, yes, sir. We are free only after this.
You are free after this?
Yes, sir. We are having class from 4:30.
4:30?
Yes, sir.
So can you just extend this?
So you can extend the class now.
Okay, so let me check. We can extend the class, maybe better. Okay, so I am trying to extend this class. Okay, maybe I can take 5 minutes break and then I can up till 4:20, maybe possible. Okay, okay, so let me check how far I can go. Okay, so I think I can record a fresh